good to be with you again. So I'll start with a quick recap. Every session, we start with a quick recap of what we discussed last time. But before I do, in the Q&A session, I wanted to make sure everyone is aware you can send questions in the chat if you want to. And you can send them directly to me as well if you want to just do it on a one-to-one basis, and then I can raise the question for the group. Okay, so you can either put your hand up and speak, or you can put it in the open chat, or you can just send it to me separately if you want to. Okay, so we start with a recap of what we discussed last time. So we began by looking at understanding what can we learn about the world around us as a starting point towards us understanding the nature of reality and the existence of God, or what the nature of God is. And we discussed how from physics we've learned that the universe is very ordered and it can be understood to behave according to certain laws. And those laws can be expressed beautifully using mathematics, and they are very comprehensible to us. We can understand them, and we can use them to make very, very accurate predictions, which are then confirmed with experiments, showing that we do really understand what's going on, and it shows that we have really got a universe that is understandable, is comprehensible. Okay, so then we started to raise the questions that come from this. Why are there any laws to begin with? What is their origin? Where do they come from? And then, these are just sort of mathematical laws. What is it that breathes fire into them to make a universe for them? Otherwise, they would just be concepts. Why is there a real universe following those laws? What is it that breathes fire into them? And we'll discuss a lot more about this in the third part of the course, where we get into philosophy. But for this part, we're just collecting information about the nature of the nature of the universe, how nature behaves. Okay, that's what we are discussing at this point. And what we said was, as a preliminary discussion, we can see that there are generally two viewpoints about these questions. Okay, the first viewpoint, which is my viewpoint, is that this is all suggestive of an intelligent mind that has designed these laws and brings them into being. Okay, it takes extremely advanced minds just to discover these laws, to understand the laws. How can they not have an intelligent mind as their source? That's the way I would put it. And that source also would be a being, or a source of being, that would actually bring them into existence. But there are other viewpoints, other ways to interpret where these things come from. And the common one out there is called the multiverse viewpoint, which says basically, look, there are billions and billions of other universes completely separate from our universe, okay? And each of those has their own laws. And so there's nothing really special. We just happen to be in one which has these laws that are mathematical and comprehensible. So there's just billions and billions and billions of universes out there, even though we have zero evidence for those laws, for those universes. And in fact, it's impossible for us to ever interact with them, because these are completely separate universes. So it's not only there's no evidence for that, there cannot be any evidence for that, okay? Because they are totally separate from each other by definition. But those are just two views, and there can be other views, and we can discuss further. But that's really where we finished last time. And there's a couple of things I just want to clarify before we go into today's topic. One is that I want you to notice something. The conclusions that I reached do not rely on a specific theory, okay? It's not that, for example, my whole argument was based on Einstein's theory of relativity or on quantum theory. And if we find out that that theory is wrong or we replace it, oh, the whole argument falls apart. No, it does not depend on any particular law or any particular theory, okay? It's using the concept of theory. It's looking at just the principle of order, predictability in the universe. Doesn't matter whether theories come and go. What we're seeing is more and more, the more we look, the more order we see, the more we understand. And as long as that's the case, then my argument still holds. The other point, though, is that comprehensibility, our ability to understand and to develop a theory and to make predictions, doesn't mean that it has to fit our intuition, our common sense. Okay, sometimes we can understand things that doesn't make sense to us in common sense terms, but when you understand it, you say, yeah, okay, that starts to make more sense. And I'll give you a couple of examples. For a long time, human beings thought the earth is flat. And they thought that the sun revolves around the earth, right? Why? Because it was common sense intuition. When we look out to the earth, we see flat surface. When we wake up in the morning, we see the sun rise from the east, and the sun looks like it's going across the sky. The earth doesn't look like it's moving, right? So what I mean is that those, when we realized that the earth is round and that the earth goes around the sun, that was not intuitive, right? It was counterintuitive. It didn't fit our common sense, but it was correct, and it did make sense to us in that way. So that's a big difference there. Intuition doesn't mean that, making sense doesn't mean it fits our intuition, okay? It's still a structure with order, and that's what matters. Okay. So with that, I want to go a little more detail into these laws and look at one aspect of them, which is really interesting and very surprising. And that is the fine-tuning of the laws of physics. Okay, now I'm going to share some slides to show. So this was where we finished last time. Right, the fine-tuning of the universe. Okay, so when we look at these laws, not only are they ordered and mathematical and make sense, we find that there are two types of incredible fine-tuning that we see in these equations to give rise to this type of universe that we have and the ability for there to be life in this universe. Okay, so I will have to go to a little bit of physics to explain some of this, but stick with me. It's not difficult, and it will be worth it when you see the results of all of this. Okay, so I'm just going to show one type of fine-tuning, which is related to the fundamental constants in the laws of physics. Okay, so the equation that you see here is Newton's law of gravity. Okay, this is how Newton understood gravity, and we have these different symbols representing, the mass of one body, let's say the Earth, and the mass of another body, which is the weight of the sun, for example. And r is the distance between them squared, right? R times r squared. Okay, that's the distance. So whatever two bodies we want to measure the force of gravity between them, we need to measure the mass of one and the other, and then the distance between them. But then we have this thing here, G. Okay, this is called the gravitational constant. And this constant is just a number. We actually have to do experiments to measure what is the value of G, so that when we plug in the mass of one and the mass of the other one, and we divide by the distance squared, we multiply by this number, and that gives us the correct force that we measure in our experiments. Okay, so G is just a number. It's a constant that we have to plug into our equations to make them work. Okay, you can think of it as the strength of gravity, the scale of it. Okay, and that number is just a constant. We use it in every time that we use this equation. We keep that number unchanged. Now, we've measured the value of G, and it comes out to be this number here, okay, 6.67 times 10 to the minus 11. And that's an example of a fundamental constant. It's a part of the laws of physics. Now, what we have, okay, so that's the first thing I need to kind of put out there, fundamental constants in the laws. Okay, that's the first thing. Now, the second thing I want to introduce is that we know from physics that the universe had a beginning. Okay, so if we look back in time, we would see that the universe actually began with a huge explosion called the Big Bang. I'm sure most people have heard about that. And in the Big Bang, everything in the universe came into existence, including space, time, matter, and energy. Everything came into the universe, into existence at the Big Bang. Okay, and then the universe has continued to expand and evolve since then. That event actually happened around 13.8 billion years ago, based on the experiments that we've done to try and measure it. Okay, and everyone's kind of familiar with this idea, right? The Big Bang theory. Now, one really interesting discovery is that, you know, what kind of explosion was this Big Bang? What were the initial conditions? Right at the beginning, you know, what was the temperature? What was the amount of energy? What was the configuration of that point, that singularity that exploded? And what we've discovered is that you need very, very, very special conditions at the Big Bang in order to have the universe that we have. If you had even slightly different initial conditions, the entire universe would either be completely empty, or it would have just simply collapsed back down on itself. Things like that would happen. But to have the universe that we have with stars and planets and life, the initial conditions had to be really very, very fine-tuned. Okay, so these are the two types of fine-tuning that I'm talking about. The first one is just about the laws themselves have these numbers in them, these fundamental constants. And then the second one is the initial conditions of the Big Bang itself. Now, when I say fine-tune, you will be amazed by just how fine-tuned I'm talking about. And we'll see those here. Okay. So we'll look at the first one in this table here, just a few examples of these fine-tuned fundamental constants, okay? I want you just to look at the size of the numbers involved. So the first one as an example is the number G that we talked about, the gravitational constant. So if G had been bigger or smaller by 1 part in 10 to the power of 35, none of this would have existed, okay? That is 1 part in 100 billion trillion, okay? That's how delicate it was. To give you an idea of this kind of number, it's a crazy number, 100 billion trillion. This is like if you had 10,000 planet Earth the whole planet, okay, and you put it on a weighing scale, and you put 10,000 planet Earths on the other side of the weighing scale, then you add 1 grain of sand to one side, that's enough to upset the balance that's there. And basically you would have had it, you would not have the universe that we have. Okay, that's one example of just one constant that has been fine-tuned. All right, there's others. There are these tiny particles that are that make part of a proton called quarks. Okay, and there's 2 types of quarks that I'm looking at here: up quark and down quark. There's very strange names for them, but just think of them these are 2 types of particles. Okay, and their mass, right? Their mass, their weight has to be very, very fine-tuned. Again, otherwise, you could not have atoms, because those protons would not be hold together. They would either collapse or they would explode. Okay, how much does it have to be fine-tuned? This is the number, 10 to the power of 21. Okay, then you have, electromagnetic force and gravity, for example. The ratio, so now not just one parameter on its own or another parameter on the ratio between 2 different parameters, right? How strong is electromagnetism compared to gravity? That needs to be within 10 to the 40. And then we have this thing called the cosmological constant, which also, again, determines how the universe will expand. That needs to be within 10 to the power of 90, right? A 1 with 90 zeros. Okay, these are examples of these fundamental constants in the laws in order to give any kind of a universe that can support life and have richness to it. Then we come to the fine-tuning of the Big Bang conditions. Okay, this number, okay, which is the initial conditions, it's called the entropy of the universe, has to be fine-tuned to 1 part in 10 to the power of 10 to the power of 123. Okay, so that's a 1 part in 10 billion with 123 zeros in it. Okay, you can't even just imagine this number. And this number was discovered by a physicist called Roger Penrose. And Penrose actually won he won the Nobel Prize last year. Okay, I was really happy to see him win it, because he's one of the most brilliant people, and he hadn't won it up to now. And he says, I don't know why people even talk about the other ones, the other constants that are fine-tuned. This one just blows away all of the other ones. You don't even need to care about the other ones. It's just an unbelievable number. And this is agreed upon. All physicists basically agree that, yes, in fact, this universe is incredibly fine-tuned to give rise to life and everything else that we see around us. Okay, now the question becomes, why is it like that, right? So back to those laws again, the nature of those laws. Not only they make sense, not only they are rational and comprehensible and beautifully expressed mathematically, but now you're also seeing that they are exquisitely fine-tuned to give rise to any kind of a meaningful universe. Okay, and once again, the 2 camps are very clear in where they stand. On the one hand, you have the people who say, look, the evidence is getting stronger and stronger, that there is a mind behind all of this that has created all of this with a purpose in mind. And the other side says, no, there are billions and billions of potential universes out there, and each of them have different fundamental constants. Each of them had a Big Bang with different initial conditions. We just happen to be in this one. And we would have to be in this one because otherwise it wouldn't give rise to life. So that's why we see. We'll discuss those things and those different viewpoints in more detail as we go along. but I just wanted to clarify this point about these laws, that they are extremely special. Okay, so hopefully that's giving you a sense of awe and wonder about this universe that we live in, and how fortunate we are, because it really didn't have to be this way. Okay, now with that, we're going to now move to looking at quantum physics. Okay, now remember why we're doing all this. We're doing this because understanding how the universe behaves can tell us a lot about its fundamental nature, its origin, and all of this has a lot of implications for our discussions about God. Okay, now quantum physics is around 100 years old as a theory that we've discovered. And it remains the most strange, weird theory that we've come up with. And it all happened when we started to study the tiniest building blocks of the world. Okay, so tiny building blocks like electrons, protons, these kind of subatomic particles. When physicists started to do experiments on these things, we started to see behavior that we did not expect and find very strange. But at the same time, we have developed a theory of quantum physics, which has been very successful at predicting what will happen in these experiments. And as I mentioned before, this is the most successful theory. So it's the weirdest theory, but we all take it very seriously because it is by far the most accurate theory we have, which shows that we do have some core understanding of what's happening. And it is a theory that has changed all of our lives. Okay, most people maybe don't realize that, maybe even if you've heard of quantum physics, maybe you haven't realized that without quantum physics, we would not have a computer, we would not have smartphones, we would not have satellites, we would not have lasers. A lot of different discoveries were all enabled by quantum physics. So imagine your lives if you didn't have any of those things now, right? If you want proof that we have a level of understanding, I'm not saying we understand exactly what's going on, but there's clearly some order there. There is some structure there that we have understood. Look at the things that you use every moment of your lives, and that's the ultimate proof for you. Okay, now with that, I sent a couple of videos in the chat that maybe hopefully you had the chance to look at, because or to watch, because it is a bit confusing the first time you come across this theory. But I'm going to play the short video that I had, which talks about the double slit experiment, and we'll just go through it together, and then we'll start to discuss. Okay, so let me share the screen, and we go ahead.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. if the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing.
Okay, so just making sure we follow along. Okay, please pay attention and stay with it so that you you enjoy the result, because it's mind-blowing. So in the normal day-to-day objects, right? He's using marbles, big balls, and firing them. We saw two lines come out on the screen, right? Two lines, because the particles, the balls go through them, and you form two. When we use waves of water and they go through the two slits, they create this interference pattern. So we see lots of these lines, right? So that's in the normal day-to-day scale of the world. That's the way things behave.
When we throw things, that is, matter, through two slits, we get this, two bands of hits. And with wave, get an interference pattern of many bands. Good so far. Now, let's
so now we're going to go to the quantum scale. So we're going to do the same thing, but we're going to do it with tiny subatomic particles, right? The whole point of quantum physics is that when we go to the fundamental level of the building blocks of matter, the things change. That's where we're going now. We're going to zoom into these tiny particles called electrons.
An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits...
Right? Remember with the marbles, when we had two slits, we ended up with two lines when we fired marbles, right? So now these are tiny particles, right? Like tiny balls. When we get two slits and we fire them through the two slits, what should happen? We should get two lines, right? That's not what happens.
We should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other.
One very strange result, which is that these little tiny balls, when they go through, we get a pattern as though it's a wave. But if it's a wave, that means it's going through both slits at the same time. How can one tiny particle go through two slits at the same time? That's very strange. But now it gets even weirder.
Physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one,
So
not
now,
both.
just us observing the electron before it goes through, so that we can know, did it go through the left slit or did it go to the right slit? Just observing it to see which one it went through changed the result. It ended up creating those two bands instead of a. Just think about this. What difference should it make whether I'm observing it or I'm not observing it? Why would that make it behave differently? Right?
The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
So hopefully you have kept up with it, but it's just truly amazing that this is how nature has been seen to behave now, okay? And we'll look at what are the implications of this? What is it telling us? What can we learn from it? To do that, I'll just share a little bit of how we got to here in the first place, okay? In the beginning, when we were doing physics, at the time of Isaac Newton, everything was considered to be very discrete and definable. Everything moved like a machine. Separate objects were independent of each other and they bump into each other, and we can understand it's very predictable. But there was no role for the observer. I mean, it didn't matter whether we were there or not. This machine would just continue to run. Human beings really didn't matter. Conscious observers didn't matter. The sun will just continue to do what it does, and so on. Okay, that was the classical physics. Then we developed relativistic physics. This was where Einstein came. Now here, the observer or the experiencer started to become more intertwined. Okay, so what we learned from Einstein is that space, space and time are not completely separate and different from each other. They are interrelated with each other. And we realized from him that time depends on how fast you are moving. Okay. If you move at a very high speed, the clock that you look at is going to move slower than it does if you stand still. That's very different to classic physics, right? In classic physics, it doesn't matter whether you're moving fast or slow, whatever you're doing, it doesn't matter. There's like this cosmic clock just ticking, right? Click, click, tick. It didn't matter whether you're moving or not moving or anything. With Einstein, already the experiencer starts to become more involved in the experience of reality. So we move fast, time slows down. That's very strange. Time is not independent. That's very strange. But now with quantum physics, we're taking it even further. We're seeing that the very nature of reality itself is changing depending on the observer, right? So we saw that if we look at the electron before it goes through the slit, it acts like a particle, like a ball. But if we don't observe it and just it goes through, we don't know which slit it goes through, it acts like a wave. So the observer is actually affecting the nature of matter itself, okay? And even this question of, a very clearly defined entity becomes very fuzzy. It's almost like it's the particle is spread out. It's kind of fuzzy. It's not this clear, defined object as before. So the big picture from all of this is, as we have progressed in physics, the experiencer or the observer becomes increasingly a part of the structure of the universe. We're not just irrelevant players in this thing. We are actually participating and shaping the way that the universe behaves. Okay, so this is one of the key outcomes from quantum physics. One of the things that we've learned about quantum physics. Now, there's one more thing I want to cover, that is called entanglement. Okay. Now, they did talk about it in the longer video that I shared, but I have a shorter version of it that I want to share here, just to give you an idea. But let me just explain what happens with entanglement. Okay, this is even if you think what we just saw was weird, this is even more weird. This is considered to be the strangest thing that we've discovered with quantum physics. Okay, and that is the following. That is called entanglement. There are ways in which we can get two particles, let's say two electrons or something, interact with each other. They become something called entangled. Then what we do is we separate these two particles by whatever distance we want. We can send one to one side of the universe and one to the other side of the universe. But somehow, whatever happens to one of them happens to the other one instantaneously. They are correlated together. It's as though they are connected. So if one of them has a certain way, is spinning in a particular way, the other one will spin in the opposite way. Okay. Even though they are totally separate, even though there's no way for them to communicate with each other, they seem to instantaneously know what each other is doing, and they do the opposite. Okay. Also a very strange discovery. So let me just show you. This is a fun way to explore it, but just give me a second to bring it up. Okay, just give me a second. Okay, so let's watch this one very quickly.
Quantum mechanics can be both strange and baffling.
Okay.
Report the quantum information stored within me from here
or here. Quantum entanglement is so strange, it's almost magical. And here to help explain quantum entanglement is special quantum magician Dan Trometer.
Thanks, Krister. Using this deck of quantum cards, Jamie and Krister will help me demonstrate the idea of quantum entanglement. First, I'll mix the cards, and then I'll have each of them mix the cards as well. But first, Jamie, please cut off about half of the cards, and then deal those into two piles. One pile for Krister, and one pile for yourself. This mixing process right now is just, in a sense, a type of shuffling, mixing into two different piles. Now that you each have your own piles, you'll mix them independently. You'll deal as many cards as you like, face down. Whenever you like, you can stop. Then you take everything in your hands, turn it over, lay it back down. Pick it up, and then do that again, as many times as you like. Go ahead. Deal face down, good. Fantastic. And you'll note that they're making independent decisions. Sometimes Jamie's just dealing a few, sometimes she's dealing more before she turns over. Same with Krister. Also note, Jamie stopped already. Krister continues to shuffle. Independent decisions. In fact, you could take these two different decks of cards, take them across the universe, and yet, because they're entangled, something very mysterious will happen. You would think that because of those independent choices and shuffling procedures, that they would have random.
Okay, so you saw
in
how
fact,
they were shuffling separately, independently, randomly shuffling their cards separate from each other, right? Now let's look at what happens.
If we look at the top card of Krister's pile, it's a black 6. The top card of Jamie's pile is also a black 6. Maybe a coincidence. Let's try it. Top card of Krister's is a red jack, red 10, red 10, 5s, 9s, 8s, 3s, 8s, 3s, aces, and queens. Because they're quantumly entangled, they have a mysterious correlation.
Okay, so I just wanted to show that. So this is the way that it happens in the lab. We actually do these experiments, we separate these two particles, and we find that whatever one is doing, the other is doing. We can predict what's happening between it, even though they're completely separate from each other. Imagine if you had two coins, okay? And you spin one coin on a table, you spin another coin on another table, okay? Separate from each other. One of them lands heads. Every time the other one lands tails. This one lands tails, the other one lands heads. Separately spinning coins, just separately spinning. How can they communicate with each other? How are they somehow they've become connected with each other? And this is called entanglement. It's been proven, and we've done it many different ways, and it is for real. And in fact, a lot of technology is actually enabled by the fact that we have this phenomenon truly does exist. Now, it is very counterintuitive for us, right? How can two separate things be communicating with each other over such long distances? So that's the two. Those are the two kind of overall results that I wanted to share about quantum physics. And we can now start to think about, what does this imply, right? What can we conclude from this? Why should I care about any of this? Well, first of all, these are the building blocks of what we are made of, what the whole world is made of. We want to understand how they behave, and they're behaving in a very strange way. But there's two clear things that we will kind of conclude from all this. But I want to try to share what the kind of thinking is these days in terms of trying to explain or develop a theory about what's going on and how we can understand it, okay? Just to kind of help you to think about possibilities of what it is. We don't know these things for sure, but this is where things are going. And this diagram, which Arif helped me with, so thanks, Arif. This is a situation that I want you to imagine, and it gives you an idea of what could be going on. Imagine a pipe, okay? If you can see this top diagram, imagine a pipe where you cannot see the middle of the pipe, okay? You can only see the one end of the pipe, and we can see the other end. We don't even know that they are connected, okay? You don't even know that they are connected. Now, if you rotate this pipe, okay, if you turn the pipe, what will happen is, if you look at it from this side, it will look like it's moving clockwise, right? And then if you look at it from the other side, it's going to look like it's moving in the opposite direction. And every time you switch the direction, this one will do the opposite, right? There is an unseen connection between the two ends of the pipe, okay? Could it be that this is what's going on in nature? In some way, we can't see the fact that these two particles are connected, but there is an unseen spatial connection between them, okay? Now, that's a very kind of simplistic way of putting it. Now we'll look at a bit more sophisticated way of looking at it, okay? Now, if we take normal space, okay? Just think about the space that's around you. Remember, we can draw space using something like a cube, okay? And these dots kind of represent points in space, okay? What we know in normal space, each point is only connected to the points that are adjacent to it, next to it, right? So if we take this point in space, okay, maybe this is where you are sitting right now. You know, the space right next to you is connected to you in these directions, but you know, the space below you, you know, by 1 kilometer or something, is not connected to you, right? Not directly. This point here that I'm pointing to is not directly connected to this point, right? It's only connected to the surrounding points in its vicinity, right? So that's the way that we understand space. That's our common sense, intuitive way of understanding space. Things are separate from each other. Something sitting here is separate from something sitting here, right? Well, the new theories that are trying to understand quantum physics at a deeper level are saying, well, maybe that's not how space is actually structured. So Stephen Wolfram, for example, has a theory called the computational universe, and he has something he uses called the hypergraph, okay? Now, I don't want to get into too much technical jargon, but all you need to know is that in a hypergraph, each point in space can have connections to any other point in space, okay? And it kind of looks like this. Well, this is one version of, just to show you an example, where each point in space can have connections with many other points in space, not immediately next. So this point here is directly connected to this point here, even though there's space in between them. They are actually next to each other. Effectively, they are next to each other. And so different points in space can be all interconnected at the same time. And maybe this is what's going on, which means, you know, these two separate particles that look like they are very separate from each other, but in a way, there's actually a direct connection between them. Okay, and this creates very interesting possibilities. It means, for example, that you right now are sitting let's say Jassim is sitting in a room. He happens to be in Istanbul right now, and I'm sitting in London. And normally we would think that, you know, the space where I am and the space where he is are not connected directly with each other, right? They're separate from each other. And there's a lot of space in between, right? And that's what we mean by separation. But what quantum theory might be pointing us to is that that's not actually the way it is at the foundation level of reality. Everything is actually much more interconnected in a way that we cannot see it from our position. Because remember, we are a billion times bigger than an atom. So it's like sitting on the top floor of a very high building. What you see on the ground floor can look very different and behave very different to somebody that's on the ground floor. Okay. Now, I covered a lot there, and I'm sure you feel bombarded and overwhelmed, but hopefully some of that was interesting. I'm just going to kind of put up a summary slide of what we covered. There was two main conclusions, okay? Two main conclusions from quantum physics. The first was that objects can appear as a wave or a particle, okay? It's very strange. Something can be a wave, okay, at the same time. And which way it is depends on how we observe it. So the observation, yeah, the role of the observer matters in quantum. And the second was this quantum entanglement. Two objects that appear separate from each other seem to be connected with each other So the concept of space and separation may need to be completely revisited because of these discoveries that we've made. And this is going to have very deep philosophical implications. For me personally, I'll describe these to you later, but what you'll see is I think this is pointing to an inherent oneness and interconnection through everything in reality. So we are not actually separate from each other. We are not individual entities. Everything is just one entity, which is actually interconnected with itself. But more on that as we go into the discussions. All right, thank you.